I came to this meeting, so I'm going to present something that really has nothing to do with quantum thermodynamics, but I think is interesting, will be interesting to many of you. So I'm Steve from the Federal University of Rio de Janeiro. So there we have a lab, a quantum optics lab, and we do experiments with entangled photons, as many of you are familiar with. So kind of the core of what we do is this right here. And then, of course, to do quantum optics, you have to do some classical optics. So, of course, we have interest in some different subjects in classical optics. Paulo Soto Ribeiro spoke about orbital angular momentum of light the other day. All of the processes which we use to create the entangled photons are nonlinear optics and so on. But so kind of what our main goal is to use the techniques we have here to study different subjects here in blue, right? So we've done, over the course of 10 or 15 years or so, a number of experiments in these kind of main subject areas. And today what I want to talk about is mutual unbiasedness and kind of just briefly mention spatial correlations of photons. So before I begin, just let me mention, so this work is actually part of a collaboration with a number of people. So I'll mention a few experimental results, and all these people, and theoretical results, all these people collaborated in one way or another. I particularly want to mention Daniel Tasca from the Federal Fluminense University and Łukasz Rudnicki from currently at the Max Planck Institute. And so this the subject I want to present is kind of these two guys and myself are sort of the main, I mean, we've been working on this for a few years. And also want to mention my student, Eduardo Paul, who did most of the experiments, which I'll present. So I want to talk, so in a nutshell, I want to talk about mutual unbiasedness in continuous variable systems and coarse graining. So what is mutual unbiasedness? As everyone knows, in a nutshell, you can say that if the eigenstates of a certain basis, eigenstates of a certain measurement operator A, return equiprobable outcomes when you measure in a different basis B, and vice versa, well then these two sets of eigenstates are mutually unbiased. So the classic example, of course, are the eigenstates of the Pauli operators, which and so the overlaps all give this constant value of 1/2, again, where I've omitted h bar. So yeah, so this is one particular example. So mutual unbiasedness is used in, I mean, it's a fundamental aspect of quantum mechanics. You don't have this in classical physics. And of course, we use it quite a bit in quantum information in protocols and so on. So just to name a few areas, of course, it's highly linked with complementarity and, of course, uncertainty relations. We exploit mutual unbiasedness to do more efficient quantum state tomography and process tomography. These mutual unbiased bases are kind of optimal at identifying quantum correlations, such as entanglement and steering and so on, linked, of course, to contextuality and other quantum information tasks. So in continuous variables, when you're an undergraduate, you learn that the position and momentum bases, eigenstates of position momentum operators, are mutually unbiased. And so in other words, if you look at the overlap between some eigenstate x and some eigenstate p, you get this value here when you're taking the modulus here. And here, I mean, this might not be true for the whole talk, but here I've omitted h bar. We can set h bar equal to 1. If there's an h bar somewhere in the talk, just set it equal to 1. So the point here is that this quantity on the right side doesn't depend on which eigenstate x or p I'm looking at. So this is, of course, known by everyone in this room and by most undergraduate physics students. What's maybe a little bit less known is that any non-parallel pairs of bases are mutually unbiased. And what I mean by this, if you take some quadrature operator, q theta, some other q theta prime, so here these two guys are linked in phase space by a rotation. And if I take it, so an eigenstate of this direction and an eigenstate of this direction and calculate the overlap, it depends only on the difference in the angle, the relative angle between the two directions. So it doesn't depend on which eigenstates in particular I'm looking at. And so, so any two pairs any two sets of bases they're non-parallel, are in fact mutually unbiased. So, okay, this is nice, and this is what happens on paper, but in the lab it's quite different. So in the lab, necessarily, so I want to make the argument here that we never actually talk about these position momentum or these phase space, these eigenstates, which I just described. We always have some sort of coarse graining in our experiment. So the first point, so I'll try to convince you of this. So the first point is that these continuous variable eigenstates are non-physical. So if you think about the modes of the electromagnetic field, these states are infinitely squeezed. So that means it requires an infinite amount of energy to produce them. So of course that doesn't happen in real life. If you think about position or momentum or so on of a point particle or even a photon, these states would be infinitely localized, which is not allowed in wave mechanics. And if you look in the complementary variable, a localized position eigenstate, of course, extends to infinity in momentum. Of course, in the lab, that doesn't happen. So what you do in order to deal with this is you define, say, localized states that are physical. So instead of x, you have some state here, f of x, where f is some function that would have, for example, mean value x and some small variance around the mean value. And so in most of even theory work you see in continuous variables considers this sort of thing in order to have a link with what happens in the lab. On the other hand, so you already have this problem when you talk about the states. On the other hand, you have also a problem when you talk about the measurements. So, for example, any measurement you do always has some amount of coarse graining, some sort of finite precision. So there's always some amount of coarse graining in any measurement you do. So a simple example, which is relevant here, is if I want to have a camera, I want to measure the position of a photon with this camera, I'm eventually going to be limited by the size of the pixels in the camera, right? And of course, every detector has some sort of finite resolution, and so on. So necessarily, we have to deal with coarse graining at some point, right? Whether we're thinking about states or thinking about measurements. And so how does this affect then mutual unbiasedness? So now if we consider, say, as it turns out, these physical states are not mutually unbiased. And in this pictorial representation, I'm trying to show you this. So if I take a state that's localized in some value x, so it has some spread in momentum, and I take some state that's localized in some value p, so it has some spread in position, and then the overlap is somehow related to the superposition of these two distributions here. Of course, if I take a different momentum state, the overlap is going to be different. So meaning that my definition of mutual unbiasedness is not valid for these two states. If I look on, so that's in terms of the states. If I look on the measurement side, if I consider, say I have some distribution in position, so p of x here, continuous, of course if it's not a point and not a delta function, but it's located in some finite region, or localized in some finite region, of course it's not going to be equiprobable, and not going to be a flat distribution in the momenta. So so that's showing this here. And then if I consider that I'm going to do these kind of coarse grain measurements with some sort of detector resolution indicated by these lines here, so I have this kind of inherent discretization from the measurement device. So I might be localized in some position bin here, and of course in the momentum bins, I'm going to be somehow distributed here. And in general, for this kind of standard coarse graining, this is not a flat distribution. So here so this would be kind of the first thing you would think to do if you'd say, okay, well this is pixels 1, pixel 2, pixel 3, and so on, right? So the point is that this kind of standard coarse graining, which the measurement device gives you, does not recover mutual unbiasedness, right? So the question which we started to ask a little while ago was, can we do something? Can we define some sort of coarse graining procedure that does recover mutual unbiasedness? And the answer, which the title of the talk indicates, is yes, we can, if we consider some sort of periodic coarse graining. And so I'll show you a particular scheme. Of course, an interesting question, I think, is if there's others. I imagine there probably are. But I'll show what we did, which I think is kind of the simplest thing you could do. So what is periodic coarse graining? So we just take essentially the real line, which would correspond to x or p or whatever quadrature variable you like. We define some period t and some bin width s. And then, of course, we choose s so that t is an integer multiple of s. So that kind of gives us this dimension parameter. I put dimension in quotes here because it's not like dimension of a Hilbert space per se, but it's the number of measurements that we will do to fill in the space. So we have the dimension parameter. And then we define essentially this mask function, m. So basically this is a function that is equal to 1 in this particular bin of interest. So here this is the mask corresponding to measurement 0. So it's equal to 1 in this region and 0 in all other regions. And of course, so with 4, and this is periodic in space, and so with 4 mask functions, we are able to fill in the whole space. Or in other words, the sum of these mask functions gives you identity, right? Yeah. So let me just mention, go on a brief tangent and kind of show you how we got interested in this coarse graining, in this periodic coarse grain in the first place. So we were doing experiments with photon pairs, and so here we generate kind of these Gaussian, almost Gaussian EPR-like states, and this is encoded in the transverse spatial profile of the photons. So technically, normally to measure these states, you have to do quite a few measurements. I mean, hundreds of measurements, thousands of measurements, and it's very time-consuming and so on. Even if you have a camera or whatever, you still have to post-process these measurements. So we wanted to find a simple way to identify entanglement. So we thought about using these kinds of mask functions, like I just described. And so we did an experiment where we encoded these masks on spatial light modulators and scanned them around in such a way. And together with Lucas, we were able to develop a kind of criteria for entanglement based on these measurements with the mask functions. So this is what the criteria end up looking like. It's not really important. Just want to show you that. So we do some position measurements with these masks. We do some momentum measurements with these masks. And then we have some upper bound, some function of the periods and the bin widths of the masks. And if we violate this, we have entanglement. So this is, so here shows a number of measurements for some different values of the dimension parameter, and we're able to see entanglement in a large number of the measurements, in others we're not. And the main point is that with this scheme, we're able to identify entanglement with as few as 4 measurements. So for us, that was nice because it's less detectors, less post-processing, and because we're poor and lazy, this was quite nice for us. Okay, so let's go back to mutual unbiasedness. So, so what we wanted to see is, so now with this periodic coarse graining, I want to show you that you can recover mutual unbiasedness, in fact. And so in order to do this, we defined some detection operators, which are just like position operators, but weighted by these mask functions. And so so here I'll talk about x and p. So we have this for position momentum. We can define some probabilities, which is just the probability of some state psi, the probability of detecting it with one of these measurement operators. And this idea of mutual unbiasedness in this sense says that, well, if I have a distribution that's localized or a state psi that's localized with respect to a position mask or position measurement, well, then it must be equiprobable when measured, or return a flat distribution when measured with the momentum masks. And moreover, that the magnitude of this flat distribution should be 1 over d, like you would expect from, say, a discrete system. So, and of course, vice versa, if we measure momentum and then look at position. So it's quite a bit more complicated than I'm talking about. So we take the mask functions, we do a long but fairly straightforward calculation, and we arrive at a condition concerning the parameters of the mask function. So we're able to show analytically that you have, in fact, mutual unbiasedness for these different measurements when the periods satisfy this condition here. So here are the periods of each of the masks. Here's the dimension parameter. This is 1. And then I have this parameter m, which is a natural number, and it satisfies this constraint here with the dimension and this other number n, which obtains these values. So, so this is nice. So so for certain conditions, we can now have mutual unbiasedness, and we have this analytically. And so because of this constraint here, you have some limits on the value of m and d. And so m here is just some parameter which we can use, which enters in the definition of the periods. So just kind of, here's this table showing you what values are allowed, what values would not be allowed. And the interesting thing, or what I want to point out, is that so for m equal 1, any dimension is possible. So Danielle actually did a proof of principle experiment of this just with classical optics. So what we did was we produced eigenstates of a position mask here, so it's a state that's localized in only these different bins. And then we do an optical Fourier transform from this plane to that plane, and we do measurements in a certain momentum mask, and we're able to change the periods and the dimension and so on. And so here shows some examples. For example, this is for dimension equal to 4. So this is for a certain period of the position mask as a function of the period of the momentum mask. So you can see, and so what I'm showing here is the Shannon entropy of the distribution, the probability distribution we correspond to the measurement results. And so if we have dimension 4, the maximally mixed, or the flat distribution would give a Shannon entropy of 2. So you can see there's some points here that indeed reach 2. There's other points that do not. That's the point of the previous result. So you can see here for this point here, 1 and 3, which correspond to m equal to 1 and m equal to 3, we have distributions that are more or less flat, equal to 1/4. So this is a kind of an optical proof of principle of this, of how we can recover this mutual unbiasedness. We also tested this for arbitrary dimensions. So, I mean, of course, we can't test everyone, but we took some values of delta theta here. So actually first is the analytical result. So we did the same sort of calculation, now considering 2 arbitrary directions, and we arrive at a similar condition, which is much like the first. However, now we have this sign of delta theta appearing here. So so taking any 2 directions in phase space, we can define these mask functions and recover with periodic coarse graining and recover mutual unbiasedness. So we have tested this also in the laboratory. So of course, as I mentioned, these 2 variables just related by a rotation in phase space. This is given by a fractional Fourier transform, which we know how to do in the laboratory with this simple optical transformation here. So just a lens placed at a certain distance between the input and the output plane. So my student Eduardo did an experiment. So again, propagating a field from one part to another. We had a preparation stage, a measurement stage using these fractional Fourier transforms. He tested, for example, for a delta theta of about 23 degrees. And here's what the results look like. Here, instead of the Shannon entropy, I'm showing the Kullback-Leibler divergence. So between our probability distribution and the ideal flat distribution. So we have this divergence is close to 0 for a certain range of the bin widths, showing that we have mutual unbiasedness. Okay, so now I think things start to get a bit more interesting. So this was always for 2 different directions in phase space. But in continuous variables, you can define up to 3 mutual unbiased species. Even, I mean, going back to the continuous variable regime. So I only found out about this a few years ago. I mean, this was shown, as far as I know, first shown in this paper here by Weigert and Wilkinson in 2008. So if you define a direction, an operator here along x, r, and s, so these are all different. These are all different by 2 pi over 3. You can show that their eigenstates are all, the overlap between all of the different pairs of eigenstates are equal. So this is, by definition, these are mutual unbiased species. And actually, they show in this paper that this is the maximum number you can have for a continuous variable system. So the natural question which we asked is, well, can we, so of course the same argument applies. If I consider now physical states that are, just somewhat localized here, not actual eigenstates, of course I lose mutual unbiasedness. So we wanted to see if this idea of periodic coarse graining will recover in this case. And it does, and it's quite straightforward to show. We had this result here for arbitrary pairs, and so we can just apply this to all the different pairs of operators and so on, and we recover these 3 different conditions for the periods. And notice now here, things have got a bit more complicated because I have different values of this parameter m here. So here I have 3 of them, m1, m2, m3. And we're free to choose them. I mean, they all have to satisfy this constraint here, but other than that, we're free to choose them. So as it turns out, for 3 directions, I can again choose all these m's equal to 1. Okay, thank you. So we did an experiment. My student Eduardo did an experiment where he prepared all the different, prepared eigenstates of all the different periodic mask functions and then measured in the corresponding the unbiased bases. So here, so here are all the 6 different combinations. This, I guess, is for dimension 7, and they're all within experimental error fairly close to the flat distribution, which should be here. So we were able to verify this for a number of different of dimensions, I guess from 2 to 10. And so this was quite nice. And so, I mean, the main goal here is now we can use this for, we hope to use this for quantum information protocols and also detection of entanglement and so on. So let me finish. Everyone is hungry, I'm sure. I am. To talk about what we're currently working on. So, of course, the first question, so we showed that it works for 2 variables. We showed it works for 3. The question is, well, how many of these periodic coarse-grained mutually unbiased measurements can we perform on, say, like a single continuous variable qumode? Yeah. And so, of course, this, let me go back one. Yeah, so the starting point, so we did some work on this, and I just want to tell you where we are right now. This is a work in progress. So we have this general condition for 2 arbitrary directions, and then, of course, as the case of 3 directions implied, you just have to kind of apply this pairwise and see what sort of constraints you come up with. And so we were able to show some of the following results. So if I want all of the different values of m for all the different pairs of directions I'm looking at, if I want them all equal to 1, I can have at most 3 mutually unbiased measurements. So I'm using this kind of this terminology here. So MUMs. So I can have at most 3. So we can show that analytically, and that follows from essentially from this. If you consider a higher number of measurements and you look at these conditions, you can convince yourself that this is the case. And we have analytical proof of this. If you want to think about these different the dimension parameter. So if you choose a dimension parameter that is an even number, well, then again, you can show that you have almost 3 MUMs. And again, this follows from this condition here. And so what was kind of more recent, which we're working on, is so if the dimension is odd, we can show that actually more mutually unbiased measurements are possible. So here's an example of one that works for 6 directions. So and it follows sort of this arrangement of the vectors and so on. And this is, again, so here we have all the different pairwise conditions that we have to satisfy. Yeah, and so I don't want to say anything more. I mean, we have some more results, but it's kind of pretty fresh. And so if we want to talk about that not being filmed, I'll talk about it with you later. I'm not sure of the results. I mean, we have some indications. So what I think is interesting here, I mean, is that so when we have even dimension in this system, in this scenario, it seems like the number of MUMs is more or less like in continuous variable system. We have at most 3. Whereas when the dimension is odd, it seems to behave more like a discrete system. I mean, we have more measurements, and I can tell you, I mean, I have confirmed that for for dimension 5, 7, 11, all prime numbers, we have in fact d plus 1. So that's something that you kind of expect from the discrete case. Not that there's necessarily a relation between the 2 things necessarily, but the first thing you want to see if it does behave like a discrete system. So that's the kind of thing we're working on. And again, this is all work in progress, and we're trying to design an experiment to investigate this sort of stuff. Okay, so just to conclude, so my main point here is that in continuous variables, we do not, in the laboratory, we do not have mutually unbiased measurements, but we can indeed recover this if we define this periodic coarse graining. I showed these results in experimental and theoretical results for 2 and 3 phase space variables. I think this is interesting because we have this dimension parameter, which, I mean, again, is not a dimension of a Hilbert space, but is a dimension of our measurement device. And I think this is I think it's quite interesting to investigate more measurements and see what we can do with this, and if it's, I mean, the big question is if this is useful for something later on. We expect there should be some sort of correspondence with the discrete variable case, but already there's some indications that they're not, of course, they're not exactly equal when we consider in regards to this dimension parameter. And of course, well, I already showed you there's this application in terms of identification of entanglement. I think it might also be interesting in tomography or partial tomography of, say, a continuous variable system using these these coarse-grained measurements, possibly other quantum information protocols and so on. So, okay, my time's up. I'm finished, but I just want to let you read this slide and do a 10-second commercial for the Parachi Quantum Information School and Workshop, which I guess is the, Marcelo help me, this is the 7th one? Oh, no, right there. Yeah, 7. It's right there, VII. That's, and I learned that in school. That was 7, so yeah. Yeah, so there are a number of interesting speakers, and some of the organizers, or one of the organizers is here right now, if you want to ask him more. Okay, thank you.
Questions? No questions?